right, hello, whoa. Wait, hang on. Let's mute that. Hello and good afternoon for our last lecture of the first half of the summer session. Whoa, that was loud. Hope you all are doing well. I am pumped for this new thing. Product placement moment. It's a lemonade. It's like a lemon black tea spindrift, which Costco got in a pack of 8 billion, or I got in a pack of 8 billion from Costco, and it is refreshing and lightly caffeinated, and hopefully our lecture will be as well. Oh shoot! Speaking of lecture, let me pull up our lecture notes, my lecture notes. So a bit of news. So I was looking at where we are. We're gonna pick up with the example that we ended with. It is Carolyn. It is really good. You should grab some if you get the chance to. I think Trader Joe's probably has some too. So a bit of news. As I'm sure you know, this weekend is the 4th of July. This is 4th of July weekend, and hopefully you have some fun things planned. I know we don't have an exam, and that's on purpose. So I was looking at the schedule of classes, and because I was like, the academic calendar. I was looking at the academic calendar because I was like, oh, I wonder if they give us any days off for 4th of July. And turns out they do. They give us the Friday before the 4th off. Isn't that nice? We don't have to have class tomorrow. I was like, that is a ripoff. Because we don't have class on Friday anyway. But here's the cool thing. We are, I was looking at where we are kind of in lecture, and we're actually a lecture ahead of where we should be. We're a lecture ahead of where we should be, and so, and in addition, we're in chapter 7, right? So the material that we're covering now would, is not going to be on the second exam. So because we're a lecture ahead, I'm going to give us a little extra time this weekend. We're going to have no class on Monday to just make our weekend off last a little bit longer. So this is Monday. We'll be back at it on Tuesday with lecture and office hours, and the kind of my reasoning for this is if I was going to lecture on Monday, it would be on more chapter 7 material. Since we're already a lecture ahead, then it's all we would be doing on Monday is just covering more material that would end up on exam 3. So we'll be back with the normal Tuesday. There'll be lecture and then office hours. The nice thing about Monday is we don't miss an office hours, and that's really kind of the open forum time. So we are taking Monday off because all we'd be doing Monday is just more chapter 7 material. So anyways, and I'll post an announcement on Canvas about that a little later today, just so that everybody gets the news. I know everyone doesn't watch lecture live. So anyways, so hopefully we'll all be able to enjoy a little kind of extended 4 days off, and then we'll come back and hit things on Tuesday, which is 7th. Okay. So that being said, let's go ahead and dive in to some more Chapter 7. Okay, so let's see. So we left things where, with an example, right? We had an example where we were given, you'll notice if you go back and you look at the previous slide, we had been given in a word problem, we had been told, given an initial pressure, right, of 1.3 atmospheres, we were told that the sample of gas had, hang on, I may have confused things in my notes. I'm just gonna double check where we left it really quick. Okay, an initial pressure of 1.3 atmospheres, an initial volume of 2.5 liters, and then we were told that the volume expands to 4.0 liters, and we're asked what pressure the sample of gas would have at its new volume. All right, and the tool that we have to solve this is our equation that we developed. The initial pressure times the initial volume of a sample of gas is equal to its final pressure times its final volume. And when you look, we have initial pressure, initial volume, and final volume, so we can solve for final pressure by dividing both sides by final volume. All right, this changes our expression. Now we have final pressure isolated on one side of the equation. And now we can plug our values in. Our initial pressure is 1.3 atmospheres. Our initial volume is 2.5 liters. Then our final volume is 4.0 liters. One thing you'll notice, and this has to be the case, so I don't know if you're in the habit of including your units in the problem as you work it, but I highly recommend doing so, because you'll notice that here we have liters in the denominator and liters in the numerator, and those two cancel. If you have different units, then we'd have to do a unit conversion. All right, and plugging them into the equation shows you whether or not they cancel. In this case, they do. We're left with atmospheres, which is good because we're solving for pressure. All right, so here, let's see, I'm pulling up my calculator. 1.3 times 2.5 divided by 4.0. And my calculator is giving me a value of 0.8125. Now, we just did multiplication and division, so we can keep, let's see, all of these have two sig figs. We can keep two significant figures. This 2 will round down, so our final answer for final pressure will be 0.81 atmospheres. That is the correct value with the correct units and the correct sig figs. So hopefully that is the answer you got as well. And this is an example of how to use this problem. Now, this particular equation, has a name, and we're about to derive a bunch of tiny equations that all have their specific names. You do not need to know the name of any of these, okay? I'm never going to ask you, use Charles' law to solve, like, I believe it's useless information. So all you have to do is know how to use these equations. You don't have to know, like, oh, this one's Charles, or this one's Boyle's law, this is Avogadro's law. Don't even trip. Okay? Okay, so this is the conclusion of how pressure relates to volume. We still need to explore how pressure relates to temperature, and pressure relates to the number of moles in the sample of a gas. But let's look at pressure and temperature. All right? So I want you to consider two samples of gas. The first I'll call sample A, and the second I'll call sample B. All right? And we're going to say sample A has, let's give it 3 moles of gas, just like before. And sample B will also have 3 moles of gas. They're in containers of equal volume. But let's say sample A is at a temperature of 25 degrees Celsius, and sample B is at a temperature of 100 degrees Celsius. All right, which sample of gas would you expect to experience more collisions, A or B? All right, and if you think about it, B's at a higher temperature, right? That means kinetic theory of matter. Higher temperature means those molecules, those particles are moving at faster speeds. If they're moving at faster speeds, they're going to have a lot more collisions with the walls and with each other. So B, sample B will have more collisions than sample A. Right, more collisions, which means it will have a higher pressure. All right? Higher pressure. That means that the pressure of a gas is directly proportional to the temperature, right? When the temperature increases, pressure increases. When the temperature drops, pressure drops. Now we learned all about this proportional to symbol. We know that if we want to turn that proportional to, that alpha, into an equal sign, we need to multiply one side of this equation by a constant number. Simply, the reason being, pressure has units of atmospheres, temperature has units of Kelvin. All right? And so if these two are going to be equal, we know that atmospheres pressure isn't equal to Kelvin, temperature. So we need a constant number to have units that will cancel Kelvin and leave us with pressure. All right? Now, we can take this equation, pressure is equal to temperature times our constant number C, and we can algebraically solve for what that constant is if we multiply both sides by 1 over T. All right, temperature cancels temperature. And we get an expression that says pressure, the pressure of a gas, divided by the temperature of a gas is equal to this constant number, whatever it is, all right? And just like with the previous example, we do not need to know what that constant is to be able to use this expression. Here's how. If you have the pressure of a gas, let's say it's at an initial pressure of something, and you divide it by its initial temperature, it's going to be equal to that constant number. Well, if the pressure of the gas changes, so will the temperature, and when you divide the second pressure of the gas, that final pressure, by the final temperature, it still equals that constant number. So we do not need to know the identity of the constant to be able to use this equation. Oops, sorry. It should be a 1. To use this equation to solve problems like that. Could I please go over the blue part of the equation again? C is a constant number. That we have not identified. Susan, absolutely. Okay, so Kirk, quick request. I'm going to, well, here, hang on. I'm going to redo this part with the algebra. I'm going to spell that out with a little more detail on the second page. Yeah. So we just call it a constant C. Okay, so we had, Susan, this expression where the pressure of a gas is equal to the temperature of a gas multiplied by a constant number C. We don't know what C is, it's just a constant number that'll correct the units, that'll cancel Kelvin, leave us with atmospheres. Now, what I'm going to do here is I'm going to solve for that constant number. All right? I'm going to solve for that constant number C, and to do that, I need to move temperature from the right side of the equation to the left side. All right? And to do that, I need to multiply my right side by 1 over temperature, so temperature will cancel with itself. But then I have to do the same thing to the left side of the equation. All right, so as of right now, temperature will cancel with temperature, and that leaves us with 1 over T times P, and this is the same thing as P over T, right? Pressure over temperature. And that is equal to our constant number C. All right, so that's how we get the expression that this expression right here. And this literally means, all right, here's the important thing. What this equation means is whenever, that is correct, Susan. I am just dividing both sides by T. And here's the significance. Whenever you divide the pressure of a gas by its temperature, it will always equal the same number. Yep, Jen, it is totally similar to the density calculation. Okay, so this gives us this new equation. P1 over T1 is equal to P2 over T2, and we can use this equation to solve problems like the following. So consider the following example that I have cooked up right here. A gas has a pressure of 4.81 atmospheres at 25 degrees Celsius. What will the pressure of the gas be when it is heated to 98 degrees Celsius. All right. Now, you'll notice in this problem that we're given initial pressure, initial temperature, and final temperature. And we're asked, what will the pressure be? All right, we're asked to find P2. So you may be going initially, okay, this looks like a job for Superman, right? For P1 over T1 is equal to P2 over T2. And it is. If you're thinking this, you're totally spot on, 100% correct. There's just one thing you need to be aware of, all right? There's one thing you got to watch out for. Whenever you're using this equation, your temperatures must be in Kelvin. All right? They always have to be in Kelvin no matter what they are. All right? So anytime you're given degrees C in a gas law problem, you need to do a unit conversion to convert those degrees Celsius to Kelvin. And here's the unit conversion. It's not nothing too tricky. It's you take your degrees Celsius and add 273. That converts it to Kelvin. All right. The reason why they have to be in Kelvin is because Kelvin is a absolute temperature scale. What that means is something will never be at 0 Kelvin. You can't get to 0. It'll always be a positive number. And you'll notice here temperature's in the denominator. And what happens when you divide by 0? Right? It's undefined. If you've had calculus, you know it approaches infinity. So you can never divide by 0. And that's why you always have to convert from Celsius to Kelvin. These equations only work when you use temperature in Kelvin. So let's real quick do some unit conversion. So 25 degrees C plus 273 will be 298. When you look at your sig figs, my last sig fig for 25 is in the ones place. My last sig fig for 273 is in the ones place. And my answer has its last sig fig in the ones place, so I don't need to round. When I look at my final temperature, I take 98 degrees C and I add 273. So 98 plus 273 comes out to be 371 Kelvin. And again, when I look at my sig figs, ones place, ones place, ones place. No rounding necessary. All right. Now that I have these numbers locked and loaded, we can do some algebra and calculate our answer. So let's take our equation. P1 over T1 is equal to P2 over T2. I'm actually going to move this a little closer to center. All right, now we need to, what are we solving for? Final pressure. We need to isolate final pressure on one side of our equation, so we got to multiply both sides by final temperature. Temperature cancels, and we get final pressure is equal to initial pressure times final temperature divided by initial temperature. All right, so our initial temperature is 4.81 atmospheres. times our final temperature, which is 371 Kelvin, divided by our initial temperature of 298 K. All right, so let's crunch our numbers. Let's see here, 481. 41 times 371 divided by, hang on, 4.81 times 371. Still big, but not insane, divided by 298. All right, so our, my calculator is giving me an answer of 5.98828. It keeps going. We don't have to, because one thing you'll notice is that we have 3 sig figs for each of our numbers, so we need to round to 3 sig figs, making our final pressure 5.99 Kelvin. Correct units, correct value, correct sig figs. Yep. That is Corinza, that is totally solid. You can always plug in the numbers first, and then move them around. Susan, great observation. Kelvin do cancel. You'll notice that Kelvin's in the denominator, Kelvin's in the numerator, so they do cancel. Oh, okay. Now I get why you're asking. Why the heck do I have Kelvin down here? That is a total brain fart on my part. That should be atmospheres, right? Should be 5.99 ATM. This is me after going, this is why I always plug in the units, because it keeps me from getting confused. Yeah. Kate, you got it. Yes, and Peyton, totally. Yeah, Jen. Susan, Kate, and Peyton, awesome job catching me in my mistake. You can always plug the numbers in first. The math works either way. I kind of, as a human, favor moving around the variables first. And if you want to know my honest reasoning why, it's because I'm lazy. It's less writing to write P than to write 371K. But you can totally plug the numbers in first and then do the algebra. It works out the same either way. So don't even trip. Either way is totally acceptable. Yeah, totally. Thank you, Corinza. That was super helpful. Illuminating the problem like that. Definitely, yeah. Honestly, I mean, this might sound weird. There's plenty that I miss about in-person instruction, right? I miss, I can't look out into a room and see faces and see if I make sense or not. Like when I'm teaching a class, I can look at all of your faces and I can instantly tell who gets what I'm saying, who doesn't get what I'm saying. And so there's these nonverbal cues I can pick up on, like, oh, I need to slow down. People are looking like they're falling behind, or like people are jiving, whatever. I totally miss that. But one thing I have to say that I like better about online instruction is for the humans who tune in live and comment in the chat. I find that there's way more engagement with the material and with each other and me in the live chat than there ever was in the classroom. And part of it is audio, right? Like, when you're in a classroom, there can only be one person talking at a time. Whereas here, I'm talking, but you guys can all be like popping stuff in the chat, answering each other's questions, helping each other out. Oh my gosh, Brianna, that's awesome. Yeah, I mean, you can show me your faces through emojis and little kittens crouching into boxes, which you can't do in lecture. But I really do enjoy how everybody kind of engages with each other, and all that. So, like, just awesome job as a class. You guys rock. Okay, Jen, you're getting a different answer. Let me double check my numbers. But then I have an idea. Oh yeah, that's definitely it. But let me try something. Tones. Huh. Yeah. Peyton, I totally agree. It's really fun being able to teach class in PJs. And like I like, you know, well, I mean, I'm not rolling out of bed at noon, but you know, like I'm taking care of a baby all day. I don't have to like get up and get dressed. I just have to make sure I'm presentable from the waist up, right? And nobody has to know whether or not I'm wearing dad sweats. Okay, awesome. Jen, I was just about to start typing, but you sorted it out. Well done. Okay. So this is how pressure relates to temperature. The last quantity we have to look at, to kind of investigate, is how does the pressure of a sample of gas relate to the number of moles in said sample. Dude, well, so you want to know what's funny about my my palm tree hair is it believe it or not, it actually has been taken out, but when I do, it just stays. So like, see, there's now it doesn't have a thing in it, and it's still just hanging. So yeah, it doesn't really need this, but I do it just so that it doesn't flop around in my face. Yeah, I don't know if this is like a midlife crisis thing or whatever. I used to have like long hair, shoulder length, like super hippie hair, and then I got a haircut, met my wife like within 8 months of it, so she's only done the short hair version, but then she was like, you might look cool with like a top knot or a man bun, so I got a license to grow some of it out, still short on the sides, but I don't know, we'll see where this thing goes. It's a new experiment. Okay, what were we talking? Oh yeah, pressure and moles. Just as a quick FYI, N. Oh, want that in black. So N is the symbol for moles. It's there's a palm tree emoji. Okay, that's my new online persona is going to be that palm tree emoji. Oh, Peyton, funny story. So am I. Wait, here we go. Okay, So N is the symbol for moles, and if you're wondering why, it's because M is equal to mass. So M was taken, so they just gave moles N because it was one letter away. All right, now let's think about how. Yes, moles. Moles are our friends, little furry dudes. So consider two samples of gas, all right, A and B. Same volume. Both of these are chilling at 25 degrees Celsius, right? Same temperature. Let's say sample A has 3 moles and sample B has 8 moles of gas, right? And if you ask yourself which one will experience more collisions, the answer is B, right? There's so many more particles in there, they're going to be bouncing off each other, bouncing off the walls. Way more collisions. In sample B. And as we know, more collisions equals higher pressure. That is the ugliest P in the world. I thought I'd just be able to live with it, but I can't. More collisions equals higher pressure. So the pressure of a gas is directly proportional to the number of moles present in that sample. And as we know, we've done this trick several times now, which several times is the boy band from Gravity Falls. If you've never seen that cartoon, you owe it to yourself. It's on Disney Plus. Probably, it's not even one of the best cartoons I've ever seen. It's one of the best TV shows. It's like X-Files for kids, and it's amazing. Tons of talented vocal actors participated. Check that out if you don't know Gravity Falls. But there's a boy band in there called Several Times. We've done this whole thing several times, right? Pressure is directly proportional to moles. Okay, does higher pressure create higher temperature? Susan, great question. And here's the thing to remember. Temperature can change the pressure but pressure can still change when temperature is the same. If moles and or volume is changing. Friends, it is so cool. I enjoyed it as an adult. It was a while ago, actually, but yeah. Anyways, so Susan, here's the thing to remember: a change in temperature will change the pressure, but temperature isn't the only thing that affects pressure. What we're learning here is we're learning how temperature affects pressure, how volume affects pressure, and how moles affects pressure. So here, the volume is the same for both samples. The temperature is the same. The only difference is there are more moles in sample B, and more moles means higher pressure. Is what we're exploring right now. Okay. So let's see. So we have this expression: pressure is equal to moles times a constant number. We can then solve for that constant number, right? Dividing both sides by n. And that gives us an expression the pressure of a gas divided by the moles of that gas are equal to a constant number C. Let me think. So Susan, pressure can change temperature. It just depends upon the conditions that the reaction is set up in. So, yes, they totally do affect each other, but you can set up two things to where the temperature will remain constant. So, for example, if you put a reaction inside a mixture of ice and water, that reaction will remain at 0 degrees Celsius because you've set up conditions to keep the temperature constant. So there's different ways you can control your reaction, your conditions. You can keep everything at the same volume or the same temperature or same amount of moles. And so you can prevent certain factors from changing to study other ones. So it really depends upon the experimental setup. Pressure can change the temperature in certain contexts, but in other contexts you can hold everything constant, like if you put something in an ice bath. I don't know if that clears it up. In this instance, when we're exploring pressure and moles at a constant volume and at a constant temperature. I don't know if that is helpful. Right. And so, but the thing is, so friction, right? Rub your hands together, they warm up. Friction can totally affect temperature. But here, the only thing that's moving in this sample, or in this setup, are the gas molecules inside each container. So there's not like surfaces rubbing together per se, there's just collisions of gas particles with the surface. But we won't actually be dealing with friction in this course, because that's more of a what's the thing I'm looking for? Physics. That's more of a physics thing. All right. So we have now an expression for how pressure and moles relate to each other. We know that if you have an initial pressure and an initial quantity of moles, divide one by the other, it'll equal a constant number C. And if that pressure changes and the moles change, you divide one by the other, they're still equal to a constant number. So we now have a third equation. Initial pressure divided by initial moles is equal to final pressure divided by the final moles, and we can now use this equation for solving problems. All right, and if that won't make your head spin, I don't know what will. We've talked about so many different types of equations, and here's one more. Let's take it for a spin. All right, so let's do an example. 3.20 moles of neon gas have a pressure of 2.02 atmospheres. If you triple the moles of neon in the sample, what will the new pressure be? All right, well here, in this equation, we have our initial sample of moles, right? We have our initial pressure right here, and we've been told that we're tripling the moles in our sample, right? That the moles, our final number of moles, will be equal to 3 times the initial amount of moles, right? So that's 3 times 3.20 or 9.60. All right, so we know our final moles, and we're asked to find our final pressure. So here, and we don't have to worry about any funky unit conversions. We have initial pressure over initial moles is equal to final pressure divided by final moles. And we can solve for our final pressure if we leave ourselves enough room on the page for the algebra. If we multiply both sides by our final number of moles. So we get P2 is equal to P1 times N2 over N1. And so this will be 2.02 atmospheres times 9.60 moles divided by a 3.20 moles. And you'll notice that moles cancel the units, leaving us with atmospheres for pressure. And our final value actually comes out to be 6.06 atmospheres. And that is our final pressure. All right. Okay. So, we have been through the gauntlet here. We have dealt with, it feels like a billion of little tiny equations with each for a special situation relating moles and volume and temperature, all to pressure, right? And if you're like me, you're probably thinking, if I have to deal with one more equation, it's going to kill me. And so if you're like me, you'll hear this as bad news. I have one more equation for you. I've got one more equation for you, but this is actually the best news yet. The equation that I'm about to give you, you can use to solve all of the problems we've done today. And yesterday. So we've looked at 3 different equations for 3 different scenarios. I'm about to give you one equation that you use for every single problem. Okay, this will be the last one you need to solve all of the problem types that we've been solving both today and yesterday with gases. Oh, thank you, Jen. Thank you very much. I'll keep that up. All right, so here, this last equation that I'm going to give you combines the 3 equations we've learned up to this point. It is called the combined gas law. All right, the combined gas law. So let's look at this. We learned that the first one we looked at, right? If you took pressure and multiplied it by volume, it would equal a constant number, right? we learned that if you took pressure and divided it by temperature, it would equal a constant number. And if you took pressure, divided it by moles, it would equal a constant number. Well, turns out if you take pressure, multiply it by volume, and then divide by both temperature and moles, altogether, this equals a constant. You can combine all of them in this relationship, smush them all together, it'll equal a constant number every time. But as we know, we don't need to know what that constant is to be able to use this, because if you have an initial pressure, an initial volume, an initial temperature, and an initial quantity of moles, it will be equal to the final pressure times the final volume divided by the final temperature and the final quantity of moles. All right, this equation is the combined gas law, and it is the only one you need. One thing I want to just point out, that if you look up the combined gas law in your book, the book will have it written like this. All right, the moles are missing in the book, and there's reasons for it, and we'll talk about what those reasons are. But this is simplified. Some would say oversimplified. Simplified. Okay, this is driving me nuts. Don't know if it's simple or simple. It's with I was right the first time. Okay, so this is a simplified version, and the reason why I'm giving you the full metal version, because in Chem 400 you'll have to deal with moles in this equation, but also, even for those of you who won't take Chem 400, you're like, I'm just in for this one, then I'm out. It'll make the next step, the next section of chapter 7 that we look at, will make more sense having included moles than not. So this is the full metal combined gas law. If you see the moles missing, just know it's a simplified version, but this will help the next stage of things make sense. All right, now you can use this equation to solve tons of problems, and you can now forget all the three little equations, because this is the only one that you need. And I'd like to show you that this is the only one that you need with the following example. All right, let's take a look at this example. So a sample, oops, let's do this in black. Whoa. A sample of oxygen gas has a volume of 3.62 liters at 1.02 atmospheres and 25 degrees Celsius. If the moles of O2 remain constant, What will the sample... Oh, sorry. What volume will the sample occupy? What volume will the sample occupy at 1.98 atmospheres and 45 degrees Celsius? All right. Now, a problem like this can seem overwhelming when you first look at it. All right. You could look at this and go, I have no idea. No idea how to solve it. And every time you feel that, it's a good feeling. This is a chance. If you're sitting down and going, I have no idea how to solve this, this is a great way to simulate that feeling of being on of taking a test and not knowing what exactly to do. Step 1, take a deep breath. Step 2, let's identify what we're being asked to find. All right? What are we after? And you'll notice in the problem, it asks, what volume will the sample occupy? You notice that they ask what volume will the sample occupy, and they gave us a volume to begin with, right? This given volume is our V1, and we're being asked to find V2, all right? You're given V1, you're being asked to find V2. So we can write down, once we know what we're trying to find, we need to start making a list of our given information. We've been given V1, right? It's 3.62 liters. Let's look at the other pieces of information we're given. So we're told that this sample of oxygen gas has a volume of 3.62 liters, and we're told it has this volume at a certain pressure, right? This is an initial pressure. We have V1, we have P1, and you'll notice we're given a temperature, T1. All right? What else are we given? We're asked, what will this final volume occupy at 1.98 atmospheres, that's P2, and 45 degrees C, that's T2. Anytime you're working a problem and they're giving you initial and final quantities of gas, that means we're dealing with the combined gas law. This is a combined gas law problem. And the combined gas law is P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. All right? And if you look at what we have P1, V1, T1, we have P2, T2, and we're being asked to find V2. There's a glaring thing. There's something that's missing here. When you look at this equation, you can say all that information is great, but we've got a problem. They don't tell us our initial or our final quantity of moles. How are we supposed to use this equation? Well, let's look back at the problem. And you're right. I said they. Who are they? I'm they. I do not give you your initial or final quantity of moles, but I do tell you something about moles. Right here. I tell you that the quantity, the moles of O2, remain constant. What does that mean? If the moles of O2 remains constant, that means they don't change, right? That means your initial quantity of moles is the same as your final quantity of moles. They're equal. And if they're equal, if they're constant, that means they cancel out of this equation. All right? Anytime a quantity is held constant, whether it's moles, pressure, volume, or temperature, they drop out of the expression. And when they do, that simplifies our equation to look like this. P1 times V1 over T1 is equal to P2 times V2 over T2. And with this equation, we have all the info we need to solve for our final volume. All right? So, whenever something's held constant, it cancels out of the equation, it simplifies, we get an easier problem to do. Now, one last word of warning. We have degrees Celsius for both of our temperatures, and we have to only use Kelvin. So we need to do the unit conversion for both our initial and final temperatures. T1 will be 298 Kelvin. T2, we have to add 273 to 45, so that'll be 318 Kelvin. I'm just going to double check my math because, you know, calculators are never wrong. 45 plus 273. Yep, 318. All right, now we're ready to use this equation to solve. All right, let's start doing some algebra. We've broken it down. Let's get to work. So we have, I need to give myself more space. P1 times V1 over T1 is equal to P2 times V2 over T2. We need to isolate our final volume on one side of this equation. So we're going to multiply both sides by T2 over P2. T2 cancels, P2 cancels, and we get final volume is equal to P1 V1 times T2 over T1 times P2. All right. We know what all of these numbers are, so let's start plugging them in. We have a pressure of 1.02 atmospheres. We have an initial volume of 3.62 liters. We have a final temperature in Kelvin of 318 divided by our initial temperature, 298 Kelvin, times our final pressure of 1.98 atmospheres. One thing you'll notice is atmospheres cancel atmospheres, and Kelvin cancels Kelvin, leaving us with liters, which is good because we're solving for a pressure. All right, let's punch all these numbers in. 1.02 times 3.62 times 318 divided by 298 divided by 1.98. And the answer my calculator is giving me is 1.99000061. We can keep 3 sig figs, right? All of these numbers have 3 sig figs in them. So our answer must have 3. We round it to 1, 2, 3. And this gives us a final volume of 1.99 liters. Kate, great question. Does volume always have to be in liters? The cool thing is, even though it usually is in liters, any volume unit will work. It could be milliliters, it could even be gallons. The only quantity, any pressure unit works as long as they're both the same. Any volume unit works. The only restriction is temperature. Temperature's got to be in temperature. Turns out moles have to be in moles too. Go figure. But you can use any pressure unit in here, any volume unit in here as well. All right, and that is the answer to that Mondo problem. If you're doing these, maybe you're finding a rhythm, but you still might be feeling a bit overwhelmed. And if you are, I highly, highly, highly recommend that you check out the homework in the book. All right, this will be the chapter 7 stuff. There's a lot of repetition, a lot of practice available to you. If you feel like maybe you're starting to get it, but still a little rusty or it's still a little intimidating, definitely check out the chapter 7 homework. It'll get you the repetition that you need for this stuff. Cool. Any questions here? We're only going to be pausing for a brief 30 minutes, enough time for me to go and eat something, and then we'll be back here for another 3 hours. So let's pause now. We can all stretch our legs, kind of clear our heads, and then we got another 3 hours of chemistry ahead of us. Yay! I look forward to seeing you all soon. I'll catch you on the flip side.